All right, so yesterday we looked at these two warm-up molecules, and we said that really they're the same molecules that are just rotating in space. And we know that they're the same molecule because they have the same name. And we talked about how sigma bonds can rotate. And then down here, we said we can look at structures using the bond line notation or the Newman projection. The Newman projection is basically just looking down some sort of internal carbon-carbon bond. And then in addition, we said we can rotate these Newman projections. And I said in class yesterday, the ones I focus on are primarily the staggered conformations. So let's go ahead down here. We'll jump into our practice problem, and we'll focus on our first Newman projection. All right, so let's imagine the eyeball is looking down here. We're going to have a cross like that for the front carbon. So the front carbon right now is basically going to consist of these groups coming off of it, right? What's going to be sticking above us, meaning pointed up? The ethyl group. So I'm just going to abbreviate that ET to make my life easier. All right, what's going to be down here to the right? The methyl group, right? Because if we're looking down that bond, the methyl group's coming out towards you. If we pivot around, it's going to be to our bottom right. So we could say methyl. And that means that the remaining hydrogen would be here. All right, now the back carbon. The back carbon has what two things sticking up? Yeah, both hydrogens. And then we have an ethyl group sticking down. All right, so that works. Then we'll do our second staggered conformation. That means we need to do a 120-degree twist. So I'll pull this down, pull this over, and pull this over. I'm just choosing to rotate the front carbon. Would it be wrong if I rotated the back carbon? No. The only thing we don't want to do is rotate both carbons. Then we're just tumbling the molecule. We're not rotating a bond. All right, so I'm just going to rotate the front one. All right, where will the ethyl group be now? The bottom right. The methyl group be bottom left. Then the hydrogen right here. And then the back carbon, we said we're going to hold that one steady, which means it's not going to move during this entire process. All right, and then last but not least, we'll do another 120-degree twist of this front carbon going clockwise. All right, now what's going to be sticking straight up? The methyl group. What's going to be to the bottom right? It would be the hydrogen, right? And that means that the ethyl group will be here. And we know that the back carbon is going to be the same in all three structures. All right, so these are the three possible staggered conformations for the molecule shown. My question for you is which of these is most stable, second most stable, and third most stable? But you had a question?
Yeah, do you want us to show the arrows?
Yeah, so the question was, do I want you to show the orange arrows? No, but if it helps you, definitely do it. I just do it here to illustrate which direction I'm turning. All right, so the question is most stable, second most stable, third most stable. So check with your neighbor and see if you agree. All right, so let's do a check-in. Give me a thumbs up if you think you've identified the most stable. Does anybody want to share with me why they think their choice is the most stable? How about somebody on this side of the room? Everybody's so social today. Anybody? The first one. Why the first one? So you said the first one because the ethyl groups are on the opposite side. Why is it beneficial to have the ethyl groups on opposite side? Because they're big, right? Big things want to be far apart from one another. So I think that's great. All right. In addition, what do we call this interaction where this ethyl group kind of nudges up against this adjacent methyl group? That's a gauche interaction. So I'd say this is gauche. However, we said that this would be the most stable, so I'll just write first right here, because the large ethyl groups are on opposite sides, even though we have a gauche interaction. All right, do we have gauche interactions in the next two? Yeah, anytime we have groups running into each other that are non-hydrogen groups. So right here we've got a methyl-ethyl clash. Over here we've got an ethyl-ethyl clash. Then here we've got an ethyl-ethyl clash. And that's it, right? All right, that gives us a clue as to which one's second most stable. The last one would be second most stable. You see how in the second one there's an ethyl-ethyl gauche interaction? There's also an ethyl-ethyl gauche interaction here, but the big problem area in this one is the additional gauche interaction that it has. All right, so that tells us pretty quickly that this must be our third most stable. I will promise you that there will be a problem that looks similar to this on your first exam. So what I mean by that is if this doesn't make sense, please come talk to me. Please talk with a friend. Utilize the Writing and Tutoring Center. We need to make sure that we really understand this concept, and there's some skill builder problems too that are excellent practice as well. Yep.
To find the most stable, we look at the size of the group and which one is bigger and needs more space.
Yeah, so let's think about it this way. First thing I always look at when I'm analyzing these, when I'm analyzing the stability, is the gauche interactions. So here I highlighted all of them, right? So the question is, well, why is the first one more stable than the second place one? Well, in the first place structure, we had an ethyl-methyl gauche, where in the second place structure, we had an ethyl-ethyl gauche. Ethyl-methyl is better than ethyl-ethyl, right? Because a methyl group is smaller than an ethyl group. Yeah, good questions. All right, so your problem of the day asks you to do a little bit more with Newman projections, so make sure you practice that. All right, how many of you brought your model kits? All right, so now is the fun one. But before we do this, I wanted to do a little bit of an overview. What we're going to talk about today is cyclohexane and doing conformational analysis with cyclohexane. So let's start off with this. There are many ways to draw cyclohexane. All right, so first way is bond line. All right, so bond line version of cyclohexane. We know based on the name cyclohexane that it's cyclic. What does hex mean? 6 carbons. So we could just draw a hexagon like that, right? Nice and easy. All right, but let's imagine we want to be super duper fancy and imagine looking down this bond, and then we'll do a second eyeball down this bond. Here's where it gets tricky. We could draw this as a Newman projection. All right, so in the Newman projection, we know all of the carbons are going to be tetrahedral. So let's draw this out. And I know this might not make much sense right now, but bear with me. So this would essentially be the side-on view looking down cyclohexane. It's a little bit tricky. I'll show you a video in a second that will hopefully clarify this. So that's just looking side-on down 2 of the carbon-carbon bonds that are parallel within cyclohexane. If you noticed right here, this is an assumed CH2. And it's pointed down. All right, and then in the back, this CH2 in green right there, this is a CH2 pointed up. All right, my question is, why doesn't cyclohexane just lay flat like a pancake? Why is it adopting this kind of pointed up, pointed down weird conformation? What do you think?
Because of the bond angles with the carbon.
So the bond angles, you're saying the bond angles have something to do with it? Yeah, I think you're on the right track. If we look at each of the carbons within cyclohexane, they're all sp3 hybridized tetrahedral carbons, right? Tetrahedral carbons are not planar. So we have to account for this non-planarity within cyclohexane. All right, and now the fun one. Newman projections for cyclohexane are really tricky to draw, as you can probably tell. The one that most chemists prefer to do is either bond line or this version called a chair. So we'll draw this 10 times fast. So everybody drew that super fast, right? All right, so what we'll do today is I'll show you kind of the steps for drawing this. So don't worry if you can't draw it perfectly right now. But really, all of these are different views of the same molecule, right? Bond line is looking down, Newman is looking side on, and then chair is kind of offset at an angle. All right, so let's look at this with a video loop. All right, so let's try this a couple of times. All right, so top down is 2D, bond line, and then we've got Newman, and then we've got our chair. So let's try it again. 2D, Newman, chair. Let's do it one more time just for fun. 2D, see Newman, and then see the chair. It's all the same molecule, we're just looking at it from different angles. In this class, though, we're going to really stick with the chair and bond line structures. The Newman ones are just a pain to draw, in my opinion. All right, so let's do some art class. How to draw a chair. You're like, I thought this was chemistry. Why are we drawing chairs? All right, number one. Draw offset parallel lines at 60-degree angles. All right, so what I mean by that is we've got parallel lines, but you see how they're not level with one another, meaning this one is slightly more to the right and this one, or sorry, that one's more to the left and that one's more to the right. Does that make sense? So that's the first step. We draw these parallel lines that are offset at 60 degrees. All right, so that's number one in our art class. Number two is draw triangle ends. Above and below to connect. All right, so I'll show you what I mean by this by redoing our parallel lines. So we'll do our parallel lines kind of like we did up above. But this time what I'm going to do is I'm going to add in triangle ends. Like that. And if you want, you can even do dashed lines right here. And in fact, I'm going to be doing this a fair amount during the course. And the way I like to imagine this is like a lounge chair. So how many of you have been on a lounge chair next to a pool, right? So in a lounge chair, you have a headrest and you've got a footrest for your feet. So over here, you can imagine this as a headrest because it's pointed up. And then this is a footrest. So you can imagine a little guy laying down here, kind of reading a book or something like that. You don't have to include the stick figure, that's just for me. All right, so we've got our headrest and we've got our footrest. All right, so this is an appropriate chair conformation. It takes a while to get good at. Really, you should have a set of parallel lines on every side. So what I mean by that is you see how this line right here is parallel to that line. That should be the case. And then this line should be parallel to that line. And then we already said the original two black lines should be parallel as well. All right, number 3. We're going to add axial substituents. To carbons pointing up and down. All right, what does axial mean? Does anybody have an idea? Yeah, what is an axis? Is it normally vertical or horizontal? It could be both, but let's think about our planet. Does our planet's axis go horizontal or vertical? Vertical. So axial means vertical in this case. So let's go ahead and redraw our chair. So our offset 60-degree lines, and we've got our triangle connected pieces like that. All right, so what I mean by that is, see how each of these are pointed up? That means that our axial substituents off of those red carbons need to be pointed up as well. So I'm just going to label these A for axial. Does that make sense? So each of these have one group pointed up. All right, down here in blue, see how these carbons all look like they're pointed down a little bit? Because they're pointed down, their axial substituents need to be pointed down as well. So I'll go ahead and say axial, axial, and then the one in the back is a little bit tricky. It's actually behind, so you can have a line break to say, hey, that axial substituent is actually behind that bond, not in front of that bond. Does that make sense? So red is up, blue is down, and these would be all of our axial substituents. All right. Next part's a little bit trickier. Add remaining substituents so that they are parallel to the bond 2 positions away. Oh, sorry, I can count. 2 positions away. So you can probably tell my counting and spelling need to be worked on. All right, so let's kind of regroup and we'll redo what we've just done. So 2 offset parallel lines. Put our headrest and our footrest. We said carbons pointed up, like these ones. We'll have axial groups on them. Carbons pointed down, we'll have axial groups but pointed down. This is kind of redrawing what we previously did. But if we think about this carbon right here that I've highlighted, it only has 3 bonds. We need to account for the 4th bond. All right, so what I mean by that is we said the bond 2 positions away would be this bond right here. You see how that's 2 positions away from the highlighted carbon? Or sorry, let me do this as a highlighted carbon. See how it's 2 positions away? All right, that means that the group coming off of it needs to be parallel to that. And this is E for equatorial. All right, let's think about this position up here in green. All right, its bond that's 2 positions away is actually going to be this blue bond right here. So that means that its equatorial substituent needs to be slanted down a little bit to be in line. Does that make sense so far? All right, let's do a few more. Let's think about this one over here in orange. Where's the position that's 2 bonds away? Well, it's probably going to be this purple position right here. So we need to make sure that it's parallel like that. And then we can go to our next one. I'll just do green again up here. Maybe we've got red right there. That means that this too is going to be parallel. Make sense? I know it takes practice to get good at it. I don't expect you to make beautiful chairs on your first go around. All right, we're missing some though. The back and the front, right? All right, so now what we'll do is we'll say, all right, what about this one? Which bonds are 2 positions away? Really, either of the diagonal ones on the sides. So I'll pick one of them. So maybe this one right here. We'll try to make that as parallel as possible. And then in the back, we've got this highlighted orange carbon. I'll just make this one red right there. And we can say that would be equatorial and parallel to that line. Does that make sense? So it takes a while to get good at drawing these. I know it takes a fair amount of time. All right. When I took this course, I've told a few of you, I was 3-dimensionally challenged, and I really struggled with doing this. So what I like doing is building my model kit, right? So when we look at this, I've built cyclohexane. It's a ring, and then at every corner of the ring, I've got a tetrahedral carbon, which you can make using your model kit. And then I'm adding in colored groups onto each of the corners. But let's look on it side on. Which color is axial? Yellow? Because why? Because it's pointed up and down, at least in this picture. All right, that means that the greens are equatorial because they're pointed out in a way, they're not pointed directly up and down. Does that make sense to everybody? All right, but we know that bonds can rotate freely, right? So let's watch this. All right, in my right hand, meaning the hand where I'm motioning to right now, see how that's my footrest right there? And then my other hand right here, that would be my headrest because it's pointed up. Make sense so far? What I'm going to do is I'm going to pull my footrest up and I'm going to pull my headrest down. So now what color is axial? Green. So greens are pointed up and down and yellow is pointed out and away. So let's watch this faster. So right now greens are up and down, yellows are up and down. Greens are up and down, yellows are up and down. This is called a chair flip. I remember when I saw this, I was like, what sort of voodoo magic was that? I don't understand this at all. So let's practice this a little bit on paper. All right, so in my chair flip, I'll just make a simple diagram of what's going on here. All right, so we've got our 2 offset parallel lines. I'm going to connect using triangles here. And like I said, when I connect the triangles, sometimes I do these dashed lines here. And I said over here that this was my headrest or footrest? Headrest. All right, and then over here, we said that this was my footrest. It's not the scientific term, it's just the term I like to use when I'm imagining these. All right, so as I was describing it to you, I said, all right, during this process, we're going to take this footrest and flip it up, meaning pull it along that portion so that it's now pointed up rather than pointing down. And the red dashed line, meaning the line right here, that's kind of our imaginary hinge. So we're going to flip it along that hinge. All right? What about the headrest side? What do I do? Flip it down. All right. So really that's what's occurring when I'm working with my model kit. All right. What I want to do is something else though. So what I'm going to do is add my axial substituent here. Let me actually slide this over. I'm going to call this A. And then my equatorial substituent I'll call B. Then I'll just relabel this footrest. All right. And we want to imagine what this looks like afterwards. All right, so A we said is axial because it's pointed down. B is equatorial because it's pointed out and away. After we do the chair flip, what should happen? What should be axial? B would be axial? Absolutely. So B was equatorial in this original drawing. when we do the chair flip, it will flip to axial, and vice versa, right? What was axial will become equatorial. All right, so let's imagine what's going on. During this process, we can redraw this, but this time our offset parallel lines will be in the opposite direction. All right, so you see how this dot right here, that was our footrest. However, when we did this flip, it is now our headrest. It's just on the opposite side of my chair. So I'll say now a headrest. And then we'll say over here that this is now a footrest. All right, we know that the position right here still has two groups coming off of it. One of these groups will be axial, the other will be equatorial. Which group's axial again? B, which means that A must be equatorial. It's kind of weird to think about, right? And you can tell that in between here, I drew equilibrium arrows. So in space, you can have this and you can look at your model kit and it's going to be flopping back and forth over time. Does that mean that it's always going to be a 50-50 equilibrium? Depends. We have to determine which of these two structures is more stable. And how do you think we can maybe determine that? How did we determine it with Newman projections? We looked at big bulky groups, right? We said that big bulky groups don't want to be close to other big bulky groups. We'll do something similar with cyclohexanes. So it's a little bit weird to think about. All right. So let's make a note here that during a chair flip, your equatorial groups become axial and vice versa, meaning your axial groups become equatorial. All right, so now we got to do something that's a little bit more challenging. So bear with me. All right, let's say we're given a structure, but we're not given the chair structure. We're just given the 2D bond line. So what we need to do now is figure out how to go from a 2D bond line structure to a chair. All right, so let's take a look at this one right here. All right, in this one, I'm going to add a group right here. That's a wedge, a group right there that's a dash. And I'm going to add a methyl group right there and a hydrogen off the dash. All right, which is important to remember, right? This red dot, as I have it shown, is a tetrahedron, right? It's not planar, it's not flat. Therefore, we have to include dashes and wedges if we really want to understand all three dimensions that are going on. All right, let's do the next one. Next one, we'll do the same idea off this carbon. And off of the dash, I'm going to have my CH3, and then I'll put my hydrogen off of the wedge. Do I need to really worry about the other groups as much if it's all hydrogens? No, not really. Typically, I like to show dashes and wedges when we've got 4 different types of groups attached on there, and we'll talk more about that next chapter. All right? So let's try to name this first. What would this molecule be named? So what's the parent name? Cyclohexane. So the parent is cyclohexane. All right. We can number the ring however we want, but we want to make sure that number 1 has a substituent off of it. So I'll go 1, and then should I number going clockwise or counterclockwise? Clockwise. to minimize numbering. Okay, so what would go before the cyclohexane? Okay, so 1,2-dimethyl. All right, however, there's one other thing we haven't quite touched upon yet. You notice how the CH3 group, one's a wedge and one's a dash? What are things called when they're on opposite sides? Does anybody know? Think about fats, right? Trans, okay? So trans means that we've got groups located on opposite sides. So this would be called trans 1,2-dimethyl, meaning one of the methyl groups is pointed on the opposite side of the other methyl group. In fact, that's what we'll use when we get into alkenes, meaning double bonds as well. All right, so we've got the name of our structure. Now what we need to do is we need to think about our chair. All right, so we'll do our offset parallel lines like that. We've got our chair all worked out. Now what we want to do is number our chair. All right, you notice how in the original structure, I numbered going clockwise. In our chair structure, we should try to be consistent. So let's number going clockwise in my chair. All right, so in my chair, I'm just going to arbitrarily say that will be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Make sense so far? Clockwise, clockwise. We've got our chair. All right, off of position 1, we would have, an axial group sticking straight up and down, and an equatorial group. It's kind of out and away like that. All right, now what I want you to do, let me actually slide this down a little. We're going to imagine ourselves hovering above this molecule, looking straight down on top of it. My question for you is we're looking at carbon 1 right now, right here in both of these. Would the methyl group off of carbon 1 be axial or equatorial?
Axial.
Why axial?
Because when you lay it down, it's going to be pointing straight up.
Yeah, so in the original 2D structure, you were saying this is closer to our eye because we're showing it with the wedge. In the chair structure, we would say, well, this bond's also closer to our eye than the equatorial bond. So I would put my CH3 group here. All right, what should be equatorial off of carbon 1? The hydrogen. All right, off of carbon 2, again, we have an axial and equatorial group. My question for you is what group is going to be equatorial off of carbon 2? Let's think about it, right? Which one's closer to our eye? The orange circle or the green circle? The orange circle is closer to the eye of the little blue stick figure, right? All right, so if it's closer to our eye, does that correspond to a dash or a wedge? A wedge, all right? So that means that our hydrogen must be here because our hydrogen off of carbon 2, meaning this hydrogen right here, must be closer to our eyeball, all right? That means that the CH3 group must be down, right? The mistake a lot of organic chemistry students make when they're doing this is they say, oh, wedges are always axial. Are they? No. In the 2D structure, we saw a situation highlighted in yellow where it was axial, but then the wedge, meaning the green highlighted part off of carbon 2, is actually equatorial. So it does depend. Make sense? All right. So now let's try to think about this chair flip. I'm just going to get rid of this highlighter. We get to kind of pick. Like I did before, I'm going to imagine little hinges right here between these. I've got my footrest down here, my headrest here. All right, and I'm going to take my footrest and I'm going to pull that up. I'm going to take my headrest and pull it down. I would encourage you to try this with your model kit Make sure you can do it with your model kit. Tomorrow, bring your model kit because we'll have class activity time. We might not be able to get to it today. But let's think about this chair flip. All right, so when we do our chair flip, you see how my footrest is now a headrest? And my headrest is now a footrest. We've got these hinges kind of pointed like that. All right, in our previous drawing, our footrest was what carbon? Carbon 2. And we said we need to be consistent with numbering going clockwise. So this be 2, 3, 4, 5, 6, which means this is going to be carbon 1. All right, off of carbon 2, we're going to have an axial substituent going up, an equatorial going out like that. Off of carbon 1, should the axial substituent off of carbon 1 be pointed up perfectly or down perfectly? Down, because it's a carbon pointed down. So I'm going to do it kind of like that with a break in the line. And then the equatorial substituent would be kind of pointed like that. All right, so now let's think back to carbon 1. And again, we're still going to imagine hovering over this molecule, looking down on top of it. Off of carbon 1, we've got this substituent that I'm going to highlight in yellow and this one in green. I want you to decide off of carbon 1 what should go in the yellow spot and what should go in the green spot. Check with your neighbor. All right, so let's check in as a class. Right now, we're thinking back to the original structure, so carbon 1 right now. We're asking ourselves, all right, off of carbon 1 in the 2D bond line structure, we've got a methyl group that's a wedge, hydrogen that's a dash, but now we need to fill it into our chair. All right, so where do you think the methyl group will be in our chair? Do you think it'll be in the yellow spot or the green spot? So let's think about it. Which one's closer to our eye, the yellow or the green? The yellow, in this case, is closer to our eye, which means that this must be our CH3 group. Because we know over here that the CH3 group must be closer to our eye in the 2D bond line structure, looking straight down at it. And in this structure, it's closer to our eye than the green one, which means that the green one must be that assumed hydrogen off of carbon 1. Make sense? So off of chairs, we don't have wedges or dashes. Yeah, because when we're looking at a chair, we're already giving it perspective by doing a side-on view, so we don't include dashes or wedges on chairs at all. Good question. All right, let's think about carbon 2. Carbon 2, we have a hydrogen and we have a methyl group. The question is, where will the methyl group and hydrogen go? So let's think about the methyl group. The methyl group in the original 2D structure was a dash. It should be pointed further away from our eye. Will that be axial or equatorial? Let's think about it. Over here, we've got this position in orange and this position in purple. Which one's further from our eye? Purple. So now we can go ahead and we can say, all right, that means that the CH3 group must be further away from our eye in this one, and our hydrogen's right here. All right, so I know this takes a fair amount of work, but let's kind of check back in. So let's focus on this structure right now. All right, you see in carbon 1, the methyl group was axial. All right, let's compare this to the second structure right here, second chair structure. See on carbon 1, methyl group's not axial anymore, it's equatorial. All right, Carbon 2 in the yellow circle, that methyl group is axial, where in the green circle, it switches to equatorial. So we can see in the chair flip these positions moving. It does get hard to draw these, so do your best with them. Students always get a little nervous some exam time, and they're like, will you mark me down if my chair is awful? My answer is no. What I normally do is I give you a template chair and then ask you to draw in the axial and equatorial substituents off of it. So I'll give you both chair forms and you have to fill in the gaps off of that. So I would recommend practicing just so you get good at it when you're taking notes. But on the exam, don't freak out if you can't draw a perfect chair. Sound good? All right, we'll practice more tomorrow on chairs, and then I'll have a worksheet for you too.